Welcome in. In this video, we will be able to calculate partial pressures of individual gases that compose a mixture using Dalton's law. So far, we've been discussing gases in general. Here we'll examine, though, real-life gases that come as a mixture and introduce new calculation strategies in order to deal with these. In a mixture of gases, each component behaves independently. This is because, as we've stated before in kinetic molecular theory, our gas particles basically just get to ignore each other. If we have our total mixture, it has some total pressure, but we can also think about each individual component of our mixture, and each component will produce some partial pressure. Because our gases ignore each other, the partial pressure only depends on how much of that gas is present. Here we can introduce Dalton's law of partial pressures, which states that the pressure due to a single component is based only on the relative amount of that component present. For example, on the previous slide, we showed the breakdown of the composition of just regular air. The total pressure is 1 atm. If 78% of that is nitrogen, the fraction of nitrogen is 0.78. And that fraction times the total pressure of 1 atm tells us the partial pressure of nitrogen. 78% of our gas is nitrogen, so 78% of the pressure is due to nitrogen. Thinking about kinetic molecular theory, the more gas that's present, the more collisions that occur, the more pressure that is there because of that gas. Moreover, the total pressure of our mixture is simply the sum of all the partial pressures in that mixture. If you have a gas with a mixture of A and B and C, we can say the partial pressure of A plus the partial pressure of B plus the partial pressure of C will give us our total. If you have just two components, great, the equation becomes more simplified. If you have 4 or 5 or 6 components, that's okay, just keep adding them together. We have some example problems. In the first, we know the total pressure, and we know most of our partial pressures, so we can set up that second form of Dalton's law and solve. Here is what our equation will look like. Now we need to plug in those values. The second problem is left for you to do as an exercise, so grab your pencil and paper, see if you can figure out a good answer. Dalton's law is particularly important in lab applications where the goal is to collect a gaseous product from a reaction. Here, the technique known as collecting gas over water is diagrammed. The reaction occurs in this sealed container, and when our gaseous product is formed, it has no place to go except into this upside down piece of glassware. This glassware starts off full of water, but that water gets displaced as the gas starts to bubble in. This is a nice, elegant way to trap our gas. But there's a caveat. When water is present as a liquid, well, there's also going to be some water present as a gas. This is known as the vapor pressure. Whenever you have a liquid, there is going to be some amount of gas above it, depending on what temperature it's at. Think about pouring hot water for tea. You can see the steam rising off of it. That's that vapor pressure. If you pour cold water or room temperature water, there is still some vapor rising off of it. It's just going to be less at lower temperatures. What's nice is this is well documented and we know exactly how much vapor pressure to expect at each given temperature. So if we pop back for a second, when we collect our gas, it's not just going to be the gas from our reaction, there's going to be a little bit of water mixed in as well. Since we have a mixture of gases, we can use Dalton's Law to calculate only the pressure of the component that we care about. Here, maybe it's that hydrogen gas that we're collecting, simply by subtracting away the pressure that we expect from water. All right, it looks like we have accomplished our goal. We can calculate the partial pressure of our individual gases composing a mixture using that Dalton's Law.
Well, there we go. Thanks so much for tuning in. Hope you all have a great day, and I will catch you next time.